Hello my test tubes and welcome to another STEP preparation video. Today I'm going to be going over 2019 Step 1 question 11. So, starting straight away, show that the probability that they make a decision on the nth round is q squared plus p squared times 2pq to the n minus 1. Well, the probability that they make the decision on the nth round is in fact the probability that they don't make a decision on each of the n minus 1 rounds times the probability that they do make a decision on the nth round, which is the probability that the coins are different for the first n minus 1 round times the probability that the coins are the same for the nth round. The probability that the coins are different is going to be, either the first person gets heads and the second gets tails, or the first person gets tails and the second gets heads. So that's QP or PQ plus the other one. So that's QP plus QP is equal to 2PQ, and the probability that they get the same coins is going to be Q squared if both of them are tails, plus P squared if all of them are heads. And so the probability that for the first round they get different coins is going to be 2PQ times the probability that it's for the second round, so 2PQ, and so on until the n minus 1 round, where it's still 2PQ. And then on the nth round, we have times q squared plus p squared, because on the nth round the coins are the same, which is 2pq to the n minus 1 times q squared plus p squared, as required. Then show also that the probability they make a decision on or before the nth round is at least this. That is going to be, the probability they make it on the nth round is going to be 2pq to the n minus 1 times q squared plus p squared. The probability they make it on the n minus first round is going to be 2pq to the n minus 2 times q squared plus p squared, all up to the probability they make it on the first round, which is going to be 2pq to the 0 times q squared plus p squared. And as you can see, this is a geometric progression with common factor 2pq, and so that's good, and all multiplied by q squared plus p squared. So we have q squared plus p squared times the sum of 1 plus 2pq plus 2pq squared all the way to 2pq to the n minus 1, which is 1 minus 2pq to the n over 1 minus 2pq. And here what makes me happy is that I have 1 minus something to the n, and I am looking for something in the form of 1 minus something to the n. And what dissatisfies me is the q squared plus p squared here and 1 minus 2pq here. So what I did originally was think, maybe I should convert everything, all of the q's here into p's, and all the q's here into p's, and then see if they cancel out, or at least one of the factors cancels out. And they do, because it is indeed true that q squared plus p squared plus 2pq is equal to q plus p squared, which is 1, and so q squared plus p squared is equal to 1 minus 2pq. And so these two cancel out, and I get the probability that they make a decision on or before the nth round is 1 minus 2pq to the nth, and rewriting this in only q, we have 1 minus 2, in only p times 1 minus p, and all of this to the n. And the minimum value of this here is going to be when the maximum value of 2 times p times 1 minus p to the n happens. And the maximum value of 2 times p times 1 minus p to the n happens when p times 1 minus p takes its maximum value, because then 2 times p times 1 minus p is going to take its maximum value, and 2 times p times 1 minus p to the n is also going to take its maximum value. And p times 1 minus p is in fact a quadratic with root at 0 and 1, and so the maximum is going to be in between those two roots, and that's a half, and the x value is going to be something else. But the point is that the maximum of this thing happens at p at p is equal to a half, and so the minimum of this whole thing is going to be at p is equal to a half, and that gives the minimum of the whole thing is going to be 1 minus 2 times a half times a half to the n, which is 1 minus 2 times a half is a half and then a half, so 1 minus a half to the n, as required. So for the second part, show that the probability that they make a decision on or before the second round is at least 7/16. Well, let's find the probability in terms of P and Q of them making a decision on or before the second round. That's going to be, well, the probability that make a decision on the first round is going to be Q cubed plus P cubed, because that's a probability that all of them either choose all heads or all tails, and then the probability of them making a decision on the second round, I suggest drawing the tree diagram, yes. And here, if they're not all going to be Qs, they're either going to be heads, tails in some order, or tails, heads in some order. And the probability that it's heads, tails is going to be 3 p squared q, and here that's going to be 3q squared. And if it's heads, tails, then the tails is automatically going to become a heads, and the heads down here is automatically going to become a tails, and tails. And so the heads have two options. They're either going to become head, or head-tail in some order, or tail in some order. And same here, we're going to have tail, or head-tail in some order, or heads in some order. And to get two heads, that's going to be p squared, this 2pq, and q squared. Here we have two tails, so q squared, 2pq, p squared. And so the probability that they make a decision on the second round is going to be 3p squared q times p squared plus 3q squared p times q squared, 3q squared p times q squared, or 3pq times q cubed plus p cubed. This is going to help because the probability that they make their decision on or before the second round is going to be the probability they make a decision on the second round plus q cubed plus p cubed, which is equal to 3pq q cubed plus p cubed plus q cubed plus p cubed, which is 3pq plus 1 times q cubed plus p cubed. And rearranging this again in the form to rewrite the q's in the form of q is equal to 1 minus p cubed, we get 3 times p times 1 minus p plus 1 plus 1 minus p cubed plus p cubed, and the 1 minus p cubed plus p cubed becomes a 1 minus 3p plus 3p squared, possibly, I think. But the point is, this is a positive quadratic in p, and this is going to be a negative quadratic in p because we have a 3p equals 1 minus p. And so that means that in total, multiplying these two was going to give me a negative quartic in P. And my negative quartic is going to look like maximum, or it's going to look like a maximum, minimum, maximum in some order. And here what you can do is start differentiating to get your results, and that's perfectly valid. I don't like differentiating a differentiation, so I'm going to look at the result here for the probability, and I have 1 plus 3p times 1 minus p plus 1 minus p cubed plus p cubed, and you realise here that the curve is going to be symmetric about p and 1 minus p, meaning that it's going to be, if it's symmetric about p and 1 minus p, then it's going to be symmetric about a half, because a half is the middle of 1 minus p. And so that means that the maximum is either at a half, 1 over 2, or the minimum over here is at a half, 1 over 2. And then looking at the value at 1 and at 0, and it's going to be the same value at 1 for p. It's going to be 1 plus 3 times Q, which is 0 plus P1, so that's going to be 4, and the value at 1 is also 4, and then the value at a half, on the other hand, is going to be 1 plus 3 over 4 times 1 over 2 cubed times 1 over 2 cubed, which is equal to 1 plus, that's going to be 7 over 4, that's 4 over 4 plus 3 over 4, times 1 over 4, which is equal to 7 over 16. So the value at a half is definitely smaller than the value at 0 and 1, so it is going to be the minimum, because it has to be the thing. It has to be one of a minimum and a maximum. So it's going to be a minimum because it's smaller than the values at So it's going to be a minimum because it's smaller than the values at 0 and 1. And the minimum is 7 over 16. So it's going to be at least 7 over 16 in between 0 and 1. Thank you guys for watching, and I hope your exams go perfectly well.